The Transmission Control Protocol, TCP, provides a communication service at an intermediate level between an application program and the Internet Protocol. It provides host-to-host connectivity at the transport layer of the Internet model. TCP works with the Internet Protocol, IP, which defines how computers send packets of data to each other. Together, TCP and IP are basic rules defining the Internet. TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to fragment application data into packets that networks can deliver, sends packets to and accepts packets from the network layer, manages flow control, and, because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, as well as acknowledgement of all packets that arrive. Let's see the connection-oriented error-free communication of TCP in an example. When a web server sends an HTML file to a client, it uses the HTTP protocol to do so. The HTTP program layer asks the TCP layer to set up the connection and send the file. The TCP stack divides the file into packets, numbers them, and then forwards them individually to the IP layer for delivery. Although each packet in the transmission will have the same source and destination IP addresses, packets may be sent along multiple routes. The TCP program layer in the client computer waits until all of the packets have arrived, then acknowledges those it receives and asks for the retransmission on any it does not, based on missing packet numbers. Then assembles them into a file and delivers the file to the receiving application. The TCP three-way handshake is the method used by TCP to set up a connection. TCP's three-way handshaking technique is often referred to as SYN, SYNAC, ACK, because there are three messages transmitted by TCP to negotiate and start a TCP session between two computers. This three-way handshake process is also designed so that both ends can initiate and negotiate separate TCP socket connections at the same time. That means the connection is full duplex. Oh, you know what? We have to take a break at this point and talk about TCP flags. There are 1-bit flags in TCP headers, which are called TCP flags. TCP flags are used within TCP packet transfers to indicate a particular connection state or provide additional information. Ignoring ECE, CWR, and NS flags for now, there are basically 6 TCP flags. The SYN, or synchronization flag, is used as a first step in establishing a three-way handshake between two hosts. Only the first packet from both the sender and the receiver should have this flag set. The ACK flag, which stands for acknowledgement, is used to acknowledge the successful receipt of a packet. The RIST flag, which stands for reset, gets sent from receiver to the sender when a packet is sent to a particular host that was not expecting it. The FIN flag, which stands for finished, means there is no more data from the sender. Therefore, it is used in the last packet sent from the sender. The PSH flag, which stands for push, is somewhat similar to the URG flag and tells the receiver to process these packets as they are received instead of buffering them. The URG flag is used to notify the receiver to process the urgent packets before processing all other packets. Okay, now we can continue to talk about TCP's three-way handshake. Step 1. Computer A sends a SYN data packet to computer B. SYN data packet means the data packet where the SYN flag of the TCP header is set. Well, what does setting the SYN flag mean? That means making the SYN bit 1. The objective of this packet is to ask if computer B is open for new connections. Computer B must have open ports that can accept and initiate new connections. Step 2. When computer B receives the SYN packet from computer A, it responds and returns a confirmation receipt, the SYN ACK packet. As you understand, SYN ACK packet means the packet in which the SYN and ACK flags are set. Step 3. Computer A receives the SYN ACK from computer B and responds with an ACK packet. At this point, both computers have received an acknowledgement of the connection. With these, a full duplex communication is established. UDP is another protocol of transport layer, layer 4, used primarily for establishing low latency and loss-tolerating connections between applications on the Internet. TCP has emerged as the dominant protocol used for the bulk of Internet connectivity owing to its services for breaking large data sets into individual packets, checking for and resending lost packets, and reassembling packets into the correct sequence. But these additional services come at a cost in terms of additional data overhead and delays called latency. In contrast, UDP just sends the packets, which means that it has a much lower bandwidth overhead and latency. But packets can be lost or received out of order as a result, owing to the different paths individual packets traverse between sender and receiver. So UDP uses a simple connectionless communication model with a minimum of protocol mechanism. It has no handshaking dialogues and thus exposes the user's program to any unreliability of the underlying network. There is no guarantee of delivery, ordering, or duplicate protection. UDP is suitable for purposes where error checking and correction are either not necessary or are performed in the application. UDP is an ideal protocol for network applications in which perceived latency is critical, such as gaming, voice, and video communications, which can suffer some data loss without adversely affecting perceived quality. In addition, since it's transaction-oriented, suitable for simple query response protocols such as the domain name system or the network time protocol.